Yes, today we will discuss some fundamental or basic concepts of finite element method of structural analysis. So, about the potential energy, strain energy, and work potential, and about the principle of minimum potential energy. Now, normally in the case of structural analysis, potential energy, which is denoted by capital pi, it is nothing but the sum, SVM sum of strain energy stored due to internal stresses and work potential due to external force. So there are two things. When external force acts on a body, something like this, so internal stresses will develop. So internal stresses will develop within the body. So the combination of those two energies can be taken as the potential energy. But when you are mathematically expressing it, one will be positive, another one will be negative because they will be in opposite nature. So suppose if I take the strain energy which is stored due to internal stresses as positive, automatically the strain energy which is going to develop due to external forces that is taken as negative. So one is positive, another is negative. So therefore it can be defined as phi is equal to strain energy plus work potential, or if I take this as negative, so mathematically you can write this plus can be replaced by minus because they are of opposite nature. I will take a simple example of a spring element, something like this. A spring is attached to the fixed end here. So when some external load acts, P is the external load which acts at one of the ends of the spring at the free end, then definitely there will be some deformation or the deflection of the spring will be there. That deflection I will take it as x, and k is the spring element, a spring constant you can say, or it is also called as the stiffness which I have studied in your matrix method of structural analysis. So p is the external force. Then if I want to write the potential energy expression, so potential energy is the sum of strain energy plus work potential. In this case, strain energy will be expressed as half into k into x square, which is nothing but the kinetic energy form, minus work potential is force into distance, that is p into x. So it is now pi is equal to half kx square minus kx. This is the expression for the total potential energy stored in a spring element, simple spring element. Now, if you take the minimum potential energy case, the condition for minimum potential energy should be the first derivative should be equal to 0. That means this dou pi by dou x is the variable here. So dou pi by dou x is equal to 0. If you differentiate this with respect to x, so you will be getting half into k is a constant, spring constant is a constant, into 2x minus p. So that should be equal to 0, or in other words you can write x is equal to p by k. So this is the expression for the deformation of a simple spring element. So force divided by the stiffness coefficient. Force is expressed in Newton, stiffness coefficient is expressed in Newton per mm, so therefore it becomes millimeter. So x is expressed in millimeter. So this is from the very simple example of illustration of minimum potential energy. Now let us see one by one what is strain energy. So strain energy, once again, it is nothing but the energy which is stored in a body due to bending moment, shear force, axial force, and also due to torsion. So these things you have learnt in your strength of materials. So different expressions we will be having for the strain energy due to these things. So it may be due to bending moment in the case of beams, shear force also in the case of beams, axial force in the case of an axial member like in the case of a truss or a pin jointed frame element, and it may be due to torsion also in a twisting element. So you will be having different expressions for the strain energy stored due to these things. You have learned about all these things in structural analysis in your BE course. Now here, in mathematical form, how to write the expression for strain energy is, so strain energy can be expressed as half into integral over V is the volume, sigma transpose into epsilon into dV. So please note that here this epsilon, the sigma is nothing but the stress, linear stress. When you plot a graph of stress versus strain, so something like this you are going to get stress versus strain graph for a material. So this is the stress, this is the strain. So initially you can see that it will be linear, then it increases and reduces, then once again it increases. For example, for mind stress specimen, when it is subjected to tension test, this is the stress strain curve you are going to have. In this linear range, up to this elastic limit, this whatever area of this is there, that is called as the resilience. So of that particular material, that means it should be in elastic limit. So this from here to here, it is in the elastic limit. So once it crosses elastic limit, it goes to plastic state and permanent deformation takes place. So now here this expression we can arrive at by having this diagram. So it is half into integral over V sigma transpose into epsilon into dV. So dV represents the volume. So this is for the entire volume of the body. So if you integrate, you are going to get for the entire volume. Epsilon is the strain, sigma is the stress. So stress is expressed in Newton per mm square, as you know, and strain is expressed in, there is no unit for strain, and of course this volume is expressed in millimeter cube. So that means here, if you multiply this Newton per millimeter square by millimeter cube, you are going to get Newton millimeter. So actually you can see that this is the unit of energy. So both work and energy, they have the same units. So normally in mechanics we define work done by a force as it is the product of the force and the displacement caused by that force due to on that body. So that is Newton into millimeter. That is the unit for both work done as well as energy. So now here this stress for a three-dimensional element, it can be written like this. So if you write transpose, then it is a row vector. If you don't write transpose, it is a column vector. Please note that. So this is the vector, that is the matrix notation. So in the case of a three-dimensional element, as you studied in elasticity, you will be having at a point 6 components of stresses. Similarly, you will be having 6 components of strains also. The first 3 are the normal stresses, these 3 are the shear stresses. Here also the first 3 are the normal strains, these 3 are the shear strains. So when you have the product of these two matrices, and when it is integrated over the entire volume of the body, you are and multiplied by half, you are going to get the strain energy expression. Now coming to the work potential, the second part. So work potential, it can exist in 3 forms. That is, it is always due to the external force. External force may be a linear force or a area force or a volume force. So like that 3 ways we can classify. Due to body force means it is body force means it acts over the entire volume of the body. So it's a three-dimensional. So in that case, work potential is expressed as integral over V U transpose into F into dV. Like that you can write. So F into dV means here what happens? This U is nothing but the displacement. Please note that U is nothing but UVW. So this is how it is written. U is written. They are the displacements along x, y, z directions respectively. F is the force vector and dV is the volume expression. So F can be written as Fx, Fy, Fz. So forces acting along all the 3 directions, x, y, z directions for a 3-dimensional element. So when you take the product and when you integrate with respect to a volume, you are going to get the work potential due to body force. Coming to work potential due to surface traction. So surface traction means it is nothing but over an area. So tractive force always acts over an area. In that case, work potential is defined as integral over S. S is represented for surface. U transpose into T into ds. Here, please note that once again this U is expressed in this is once again the deformation which is in millimeters. T is the tractive force which is expressed as Newton per millimeter square, and ds is the area which is millimeter square. So if you multiply these 3, you are going to get finally you will be getting in Newton millimeter. So if you multiply all these, you will be getting in Newton millimeter. Here also you will be getting in Newton millimeter if you multiply all the three units. So because that work done will be expressed as force into displacement, like that. Now due to point load, work potential is expressed as in a discrete form. So summation UIT transpose into PI. That means here PI represents the number of point forces that are acting on the body, a linear force, into displacement vector. So here once again, at whatever point you are going to take, at those points you should have the values of the displacement and the magnitude of those forces. It is given as PI. When you take the product and when you add, you are going to get the value of work potential for a due to a point load, and when you multiply the units, you are going to get Newton millimeter, because P will be in Newtons, UI will be in millimeters. Now if you combine all these three, body force, surface tension, point load, everything, you can express the total potential energy in a three-dimensional elastic body. Elastic body can be expressed as half into integral over V sigma transpose into epsilon to dV, that is the strain energy part, and this work potential part will be having 3. I have taken negative because I have told here that work potential will be in the opposite nature as that of the strain energy. So minus will be there for all these 3. So first one is I have taken this F due to body force minus integral over V U transpose dV into F. Then due to surface traction force minus integral over S over the surface into U transpose into T into ds minus summation due to point load UI transpose into Pi. So if we add all the terms, you are going to get the total potential energy in the case of a three-dimensional elastic body. Suppose in any problem, if the surface traction is missing, then this term will not be there. If you are asked to neglect the body force component, this term will not be there. Like that, we have to decide. This is general expression for the total potential energy that is stored in a three-dimensional elastic body. Now we will come to the very important principle called principle of minimum potential energy. According to that, it states that a body which has minimum potential energy satisfies 3 conditions. One is equilibrium condition, second one is compatibility condition, and third one is the boundary condition, and the body will be stable. So stability of the body is achieved. So that means I can explain that with an example here. Consider a body of weight W, same weight W or mass M. So M into G becomes a W. So here, if you consider the body of same weight at different heights, so this is the reference of the datum. At different heights, if you consider the bodies, then definitely since it is at some height with a reference, it will possess potential energy. The potential energy of the first body is W into H1. Potential energy of the second body is W into H2 or mgh. We can take mgh. If you know the mass multiplied by acceleration due to gravity is the weight multiplied by that h. Now here you can observe H1 is less than H2. Therefore you can say since W is same, so PE1 is the minimum. So PE1 is less than PE2. So that means this body is more stable. That is the meaning of that. So both the bodies, they satisfy all the 3 conditions: equilibrium, compatibility, and boundary conditions. But since the potential energy of this body is less, so this is more stable. So this is the principle of minimum potential energy. That means, in other words, the total potential energy that is stored in a body consists of 2 parts. One is the strain energy, another is the work potential. Strain energy is due to the internal stressor that is going to develop within the body, and this work potential will be due to the external force that is acting on the body. Since they are of opposite nature, one will be positive, another will be negative, and this is a spring element example. So, and I have given the expressions for the strain energy as well as the work potential for 3 cases. For a point load, for a surface traction, for body force, and this is about the explanation of principle of minimum potential energy. Using this concept, we can always find out the deformations or unknown force, anything in the case of a bar element or a spring element, something like that.